In this segment, we'll begin a discussion of probability spaces. We'll start by defining sample spaces and events. Then we'll look at an example of an infinite sample space to see what kinds of conceptual difficulties arise in assigning probabilities to sets. We'll introduce the concepts of algebras and sigma algebras, and this will allow us to define measurable sets and spaces in general and probability spaces in particular. Now consider any non-empty set omega, which we'll interpret as the set of all possible outcomes of an experiment. We'll refer to this set as a sample space and to a point in this set as a sample point. An event is defined as a subset of omega to which a probability can be assigned. Now if omega is finite, then in principle we could assign a probability to every possible subset of omega. But if omega is infinite, then some conceptual difficulties arise in assigning probabilities to arbitrary subsets. To get a sense of the issues involved, let's take an example. Consider an infinite sequence of tosses of a fair coin. Now the sample space in this case is equivalent to the set of all binary sequences. If we think of tails as corresponding to 0 and heads as corresponding to 1, then an infinite sequence of coin tosses is just a binary sequence. Now we know from earlier in the course that this set is uncountable. Now clearly we can assign a probability to some subsets of omega. For example, to the probability that the first 3 tosses are all heads, or 6 out of the first 10 happen to be tails. These are subsets to which we can assign probabilities without any difficulty. But can we assign a probability to every subset of omega? We'll see that the answer to this turns out to be no. But first consider a closely related problem. So consider the unit interval 0, 1, open on the left and closed on the right. Each element of this set has what is called a binary expansion, or sometimes a dyadic expansion. This is just the expansion of the number in base 2, and it's just a sequence of 1s and 0s. Now some elements of the unit interval have 2 binary expansions. So for example, the number 1/2 can be represented as 1 followed by a sequence of 0s, or 0 followed by a sequence of 1s. Now the first kind of expansion we'll call a terminating expansion because it has a finite number of 1s, and we could drop every subsequent term without changing the value of this number. And the second type of expansion we'll call a non-terminating expansion. It has an infinite sequence of 1s. And I think you can see that every element in this unit interval has a unique non-terminating binary expansion. So the set of binary sequences and the interval 0, 1 are very closely connected. If we neglect the terminating expansions, then the sets are in fact equivalent. Now let's define the size or measure of a subinterval of 0, 1 to be the length of that subinterval. And let's think about whether we can extend this notion of size to non-interval subsets. Now the question of whether every subset of 0, 1 can be assigned a measure is very closely connected to the question of whether every subset of omega can be assigned a probability. To see this, let's consider some very simple events. So consider the event that in the first 3 tosses of this coin, we get at least 2 consecutive heads, which we are representing as 2 consecutive 1s in an infinite binary sequence. Now there are 3 possible ways in which this could happen. You could have tails followed by 2 heads followed by tails, or 3 heads in a row, followed by an arbitrary continuation. And you can see that the probability of this event, 3/8, is equal to the sum of the disjoint intervals shown in red in the figure. So this event corresponds to a finite union of disjoint intervals, and the probability of the event is just the sum of the lengths of these intervals. But now consider a more complex event. Take any number omega in the unit interval, and let dn of omega be the nth term in the binary expansion. Then define Rn of omega to be 1 if dn is equal to 1, and -1 if dn is equal to 0. And finally define Sn of omega as the partial sum we get by adding up all the terms Ri of omega for I ranging from 1 to n. And now for any positive integers a and b, consider the event shown on the slide. Now this event corresponds to the set of coin tosses such that the partial sum Sn reaches -a before it ever reaches positive b. Now this has a straightforward interpretation in terms of a gambler's ruin problem. So think of 2 individuals. Let's call them Alice and Bob. Alice has a budget of $A, Bob has $B. Every time tails comes up, Alice pays Bob $1, and every time heads comes up, Bob pays Alice $1. Then this event corresponds to the subset of outcomes in which Alice loses all her money before Bob does. Now if you think about this, you should be able to see that this corresponds to a countable union of disjoint subintervals. And the question is whether we can assign a probability to this event. Now clearly the answer is yes, but to do so we need to extend our concept of measure to countable unions of disjoint intervals. Now let's consider an even more complex event. So we define the subset n of omega to be the set of infinite binary sequences in which heads and tails appear with equal frequency in the limit. Viewed as a subset of the unit interval, this corresponds to what are called normal numbers. But unlike the events we considered previously, we can't express this as a union of intervals. Now the question is, can we assign a probability to this event? And the answer turns out to be yes, and the probability is in fact 1. But to do so, we need to extend our notion of measure to non-intervals. Now it turns out that we can do this, but we can't extend our notion of measure to all subsets of the unit interval, and therefore not all subsets of omega can be assigned a probability. Now let's look at this more systematically, and we'll begin by defining algebras and sigma algebras. So a class script A of subsets of omega is called an algebra if it satisfies 3 conditions. First, the class should include omega itself. Second, for any set A in the class, its complement should also belong to the class. And for any pair of subsets in the class, their union should belong to the class. And a class of subsets S of omega is called a sigma algebra if it satisfies the additional requirement that for any countable collection of sets in S, their union is also in S. So an algebra is closed under the formation of complements and finite unions, and a sigma algebra is also closed under the formation of countable unions. Now it's important to recognize that a sigma algebra need not be closed under the formation of arbitrary unions. If that were the case, then any sigma algebra that contained all the elements of omega viewed as singleton sets would in fact be the power set of omega, because any subset of omega is just the union of its elements viewed as singleton sets. So keep in mind that a sigma algebra is closed under the formation of countable unions but not arbitrary unions. Now you should verify that the requirement that omega itself belongs to the class can be replaced by the requirement that the empty set belongs to the class, or in fact that the class is not empty. And furthermore, using De Morgan's laws, verify that closure under unions can be replaced by closure under intersections. And that's in both definitions, algebras and sigma algebras. Now if S is a sigma algebra in omega, then the pair omega S is referred to as a measurable space, and any element of S is said to be an S measurable set or an event in omega. Let's look at a few examples. The smallest sigma algebra on any omega is just the class consisting of the empty set in omega. The largest sigma algebra is just the power set, the set of all subsets of omega. If omega has 4 elements, call them 1, 2, 3, and 4. An example of a sigma algebra is shown on the slide, and you can see that this is not the power set of omega. Now let's look at a slightly more complicated example. For any infinite set omega, the collection of all finite or cofinite sets is an algebra, but need not be a sigma algebra. Now what we mean by a cofinite set is simply a set whose complement is finite. So let's prove this. Let A denote the collection of all finite and cofinite sets of omega for any arbitrary infinite set omega. Now you can easily verify that the first 2 conditions for an algebra are trivially satisfied. Omega is cofinite and therefore an element of A, and if any subset of omega is finite or cofinite, then its complement must also be either finite or cofinite. So all we need to do to prove this claim is to verify that for any 2 sets A and B in the class, their union belongs to the class. If both are finite, then it obviously does. Their union itself must be finite and belongs to the class. If not, then at least one of them must be cofinite. In other words, at least one of the sets A complement and B complement must be finite. In which case the intersection of these 2 complements must be finite. And therefore, again using De Morgan's laws, the complement of the union must be finite. Hence the union of A and B is cofinite, and this set belongs to the class. So the class of all finite and cofinite sets of any arbitrary infinite sample space is an algebra. Now to see that this is not a sigma algebra, let omega be the set of natural numbers and consider a subset that consists of the odd numbers. Now this set is neither finite nor cofinite, but if you take the individual odd numbers viewed as singleton sets and take the countable union of these, you get the set of odd numbers. And so you have a countable collection of sets in A whose union is not itself a member of A. So A is not a sigma algebra. Now let's take another example. For any omega, the collection of all countable or co-countable sets is a sigma algebra. Now by co-countable, we mean sets whose complement is countable. And by countable, in this segment, I'm going to include sets that are finite. So we'll use the word countable to mean countable or finite. Now let A denote the collection of all countable and co-countable subsets of omega. We want to show that this is a sigma algebra. Now as before, you can easily verify the first 2 requirements. That for every set in this class, its complement belongs to the class, and omega itself belongs to this class. Now suppose we have a countable collection of sets that belong to this class. Call them A1, A2, and so on. If each of these sets is countable, then of course their union is countable. One of the first things we showed in this course was that a countable union of countable sets was itself countable. Now if these sets are not all countable, then there must exist at least one, call it J, that's co-countable. In other words, the complement of J is countable. And because the complement of J is countable, if you take the intersection of all the complements of the AI, that must be a subset of the complement of AJ and must therefore be countable. That's because the subset of any countable set must be countable. And remember, here we are using countable to include finite sets. Now again apply De Morgan's laws to see that the complement of the union of these sets AI is countable, and so the union of the sets AI is co-countable, and this union therefore belongs to the class. So we've shown that the collection of all countable and co-countable sets is a sigma algebra. Now this collection need not be the power set of omega, and you can see this very easily by letting omega be the unit interval and consider any subinterval, for example the set of numbers between 0 and 1/2. This set is neither countable nor co-countable, and therefore not an element of this class. Now we'll finish up this segment with a couple of definitions. Let omega be a non-empty set and let A be an algebra on omega. We say that a function p from the algebra to the non-negative extended real numbers is countably additive if the following condition holds. Take any countable collection of sets in the class A such that the union of these sets is itself in the class and such that these sets are pairwise disjoint. Then P is countably additive if the image under P of the union of all sets in T is equal to the sum of the images under P of the individual sets in T. Now note that if A is a sigma algebra, then the union of any countable collection of sets in this class must also belong to this class. So therefore the requirement that the union of all sets in T belongs to A would be redundant. But if A is an algebra, it need not be a sigma algebra, and we do require this condition. Now to finish up, let's define probability measures and probability spaces. Let the pair omega S be a measurable space. Any countably additive function P from the sigma algebra to the non-negative extended real numbers such that the image of the empty set under P is 0 is called a measure, and the triple omega S P is called a measure space. And if in addition the image of omega is equal to 1, then P is called a probability measure, and the triple omega SP is referred to as a probability space. Now we'll work with these concepts in the next segment, but I'll stop here for now.